Hi, I'm Mr. Franklin, and today we're going to be looking at free body diagrams, net force, and friction. So let's jump into it. So first thing is, a force is a push or a pull. A force causes acceleration. If something is accelerating, there must be a net force not equal to zero. If there is no acceleration, there may still be forces present, but they add up to zero net force. So we've talked about that with our DVA graphing. So we also write force, we could say force net equals positive. Acceleration is going to be positive. If the force net is negative, the acceleration would be negative. If the net force equals zero, then the acceleration is going to be zero. You could also have written down something regarding Newton's three laws. So the first law, an object's motion, an object in motion stays in motion, an object at rest stays at rest. In other words, an object's motion remains unchanged if there is no net force. You will either keep moving at constant speed or stay at rest. Then we've got the second law, F equals ma, and the third law, for every action there's an equal and opposite reaction. So those are just some things you should already know going into this video about forces. So those were covered in previous classes or videos. You may notice, remember, that we talk a lot about net force, which means all the forces added together. And today what we're going to learn about is there's a special tool we use in physics to figure out net force, and also so we can use it to figure out net force, but we can also use it to work backwards and isolate individual forces acting on an object. So we're going to start with this example. So we're going to start by looking at the forces acting on your cell phone. So you can use your cell phone, you could use your pencil, okay? But we're going to just set the phone on the table, okay? You may be watching this on your phone, so you may want to switch to your pencil, but I'm going to be writing with my pencil, so I'm going to use my phone. When we did our 7-step problems, we would draw a picture of what's happening. So we've got forces acting on this phone, so let's draw a picture of that. Here's my phone, and it is sitting on the table. Quite amazing drawing, really. Okay, so let's draw the forces on this phone. Now, if we really get down to the nitty-gritty, we could say there's the force of gravity, right? So we know there's a force of gravity pulling on the phone, but it's not just pulling on that part of the phone, it's pulling on all parts of the phone, right? Anything that has mass is pulled by other objects with mass, and in this case, the Earth's mass. And so we get this force of gravity. So every particle in this phone, don't care where it is being pulled by a force of gravity. And if we drew every single particle and every single force, that could get quite tedious. So I'm going to show you how to simplify that in a second. But there's another force acting. So if force of gravity is pushing down, what's pushing back? So we have a reaction force, which we're actually going to call the normal force, and we'll write that down in a second. But so we have the force of gravity, and we have this thing called the normal force. And it's the reaction of the table pushing back on the phone. Because the phone is sitting on the table, its weight is pushing on the table. So its weight is pushing on the table, and the table is pushing back. Okay? So, but in the same way that the force of gravity pulls all the pieces of the phone down, wherever that phone is touching, so wherever this phone is touching the table, that's where the table is pushing back. So we could draw a force at the surface of the phone where the forces are pushing back. Now, as you can see, could get quite complicated, and it's one of the reasons why Newton created calculus. It's because it actually allows us to calculate more complex things like this. But most physicists are able to do this, and partly because of calculus, but we're going to draw what's called a free body diagram. And we're going to take all these forces, okay, and we're going to sum them up and simplify them. So we have the force of gravity. So our object becomes a single dot. We're no longer going to draw the actual object. It becomes a single dot. We're going to draw an arrow representing that force. So this is particular force is gravity. Even though it's pulling on all the pieces of the phone, we're going to say this is just gravity. We're going to pretend it's a single force. If there's a single force pushing down, then we have a single force pushing back, and that's the normal force. The object is represented by the dot. The force, the arrows represent the forces. Now these arrows, they point the direction the force is going, but notice it's not where the force is actually pushing. But not where the force is pushing. So I'm going to do this wrong here just so you can see what I'm trying to say here. So we've got our phone sitting on the table. If we look at this technically, we've got the force of gravity here. But where does the table actually push back? It pushes back underneath the phone. So we could draw this arrow and then have the arrow where it's pushing up against the phone. That is not how we're going to do it. And the reason for that is this is much easier to see, because what we want to do is we want to find the net force. Force net equals, on your equation sheet, F1 plus F2 plus whatever other forces. So in this case, force net is equal to the force of gravity plus the normal force. Now we don't have any numbers, but if this phone is just sitting on the table, it's just sitting on the table, what does the net force have to be? Is it moving? No, it's at rest. So the net force has to be 0. And if you look at this, the force of gravity is in the negative direction and the normal force is in the positive direction. Then those are going to be equal to each other. But one of them is going to be opposite. So they're equal, but that's a negative number. And when you add them, they're going to cancel out. The net force is going to be 0. So that's why we actually draw it like this, where we start from the object and draw in the direction the arrow is going, even though the actual force may be right here. Okay? So be careful of that. Need an eraser. Be careful of that when you're drawing your free body diagrams. They always go away from the dot in the direction that they're pointing. Okay, so now we're gonna try another one, okay? So we've got our phone at rest, sitting on the table, force of gravity pushing down, the table pushing back. It's not moving, and that's our free body diagram. So now we're gonna switch, and we're gonna do what happens if I take my phone and now I push it across the table. So now, if I'm pushing it, there is a force, the phone is moving, and let's take a look at how and why this works, okay? So dot diagram. Not dot diagram, I'm thinking chemistry. Free body diagram, okay? So we've got our phone, it's a dot. We've got the force of gravity, still acting. We still have the normal force, and then we have the force of my push. Okay? This is the force of gravity, and this is the normal force. So you should always label your diagrams with what the forces are so we can sort it out. Now, this is something we haven't gotten a lot into, but which direction are these in? Are they in the Y direction or the X direction? They're in the Y direction. So when we add forces, net force has to be calculated using forces acting on the same axis. So only forces in the x direction, or only forces in the y direction. Now, with more advanced physics, we can actually combine the two by using Pythagorean theorem and some of our angle rules, but we're gonna try to stay away from that, except for maybe at a conceptual level. The bottom line is, if I can only add these two because they're in the same axis, they're on the y direction. So the net force in the y direction is equal to the force of gravity plus the normal force. The net force in the x direction is equal to the force of the push plus, now if we actually considered friction, friction always opposes the direction of motion. So we could have a force of friction here as well. Okay. If my phone accelerates in that direction, then the net force has to be positive in that direction. But that's a negative direction, so the net force would be negative. Now, if it's moving at a constant speed, speed is unchanging, then the force of the push and the force of friction must be exactly equal to each other and exactly opposite each other for it to be going at a constant speed. Okay, so we're gonna try another situation here. And then I'm going to give you some for you to practice. So this time we're going to take our pencil and we're going to throw it up in the air. We're going to throw it up in the air. Once it's in the air, it's airborne. I'm not actually, pretend like I'm not holding it. So I'm going to throw the pencil in the air. I'm not holding it anymore. It's airborne. What are the forces acting on the pencil? So here's my pencil. What are the forces acting? We have the force of gravity. And if there is no friction, that's it. So guess what happens? When it's going up, if there's nothing else but gravity, if there's a force of gravity, which way is this going to accelerate? So force of gravity is negative, so the acceleration must be negative in direction, which means eventually the pencil slows down, it stops, and then it comes back down. But always the change in the pencil's velocity is always in the downward direction. It's always negative. Okay? And that's what this diagram tells me. Because the force is always in a negative direction, eventually the object will stop going in this direction, turn around, and come back down, and you have a negative acceleration, force of gravity. Now, same idea though, but now let's talk about reality. I throw the pencil up. If the pencil is in the air, there's a thing called air resistance. Well, any type of resistance is opposite in direction to the motion of the pencil. So on the way up, the force of friction, so sometimes you have to draw your dot big, so the force of friction is also in the downward direction. So this is on the way up, because the pencil is moving up. The air is pushing down because it opposes the motion of the object. On the way down, we have the force of gravity, but air is pushed, but now it's moving downward, so the air resistance is opposing its motion, so the force of friction is that way. So this is when the pencil is moving down. Okay? So free body diagrams are what we're going to use to help us isolate what forces are there, to determine which direction is the object going to move. They're super useful in physics. So I'm going to give you 3 more cases for you to practice on your own. Okay. And then at the end of the video, I'm going to draw what I'm based on our class, what our answers should be, and then I will give you some work to do, more work to do on your own. So go ahead and take a look at this right here. Here are your 3 practice problems. I also have a bonus extension problem. Pause the video, work through them, and then you can take a look here in just a moment at the approved solutions and see how you did. Okay, so let's do number 4. Saturn V rocket sits on the launch pad waiting for launch. Draw the free body diagram of the rocket. So I've got a rocket sitting on the launch pad. Wow. So we've got gravity, force of gravity, and then we've got the ground pushing back on it, and that's called the normal force. Is the rocket moving or is it still on the ground? In other words, is it accelerating? Is it moving? Is it at rest? What is it? It's at rest. So the acceleration must be equal to 0, which means the net force has to also be equal to 0. What does that mean? That means the rocket's just sitting there on the launch pad. Okay, number 5. Rocket carrying Apollo 13 has entered space. Its rocket is still firing. Assume the direction of the rocket is firing and gravity are on the same axis. Draw the free body diagram for Apollo 13's rocket. Okay, so we're making some assumptions here, okay, and simplifications. But we've got our rocket. Wow, it's amazing. Didn't know you could draw a rocket, right? Okay. It has entered space. Its rocket is still firing. So which way is the rocket going to push the rocket? It's going to push it up, right? Okay, so that's the force of the rocket. We're in space, so is there any air or wind? No, so there's no friction. But it is still close to the Earth, so it's got gravity. Now, something I didn't mention earlier is the size of the arrow represents the strength of the force. So, which direction is the rocket ultimately moving? It's moving this way, so that means this force must be bigger than this force as long as it's accelerating. Okay, now you can have an object that is moving through space, but these forces are perfectly balanced, but it's still moving. That's Newton's first law. Okay, so if the rocket has a positive acceleration, then this net force must also be positive. Now, if the force of this rocket and the force of gravity are exactly equal, the rocket could actually still be moving up. Okay, the rocket could still be moving up, and then the acceleration turns into 0, and the net force equals 0, and the rocket will keep going without stopping. Okay. Number 6, Apollo 13 enters the Earth's atmosphere. There are no engines, so we've got the capsule. It's entering the Earth's atmosphere, and we're going to draw the free body diagram. And there's no engines, but there is friction, so it's coming down into the atmosphere. So we have the force of friction, and we have the force of gravity. Why do we know the force of gravity is bigger than the force of friction? Because the object is falling. Okay? So the acceleration is negative because it's in a negative direction, and the net force is negative. Kind of get the idea? Then I will post your homework problems. Okay? Alrighty, do your best on that. I'll come back and we'll talk a little bit more about normal force and friction. Thank you.